Okay. After having looked at the 3 examples of Dalembert principle, well, if you looked at those examples, they seemed rather lengthy and hard, but you see what happens here. I have this Dalembert's principle, and the Dalembert's principle is written in terms of the Cartesian coordinates. Now, the Cartesian coordinates, because of constraints, are not independent of each other. So, we have to write the entire equation, identify the independent variables, then find the coefficients of the virtual displacements of these coordinates, and that finally will be able to give or that finally will give us the equations of motion. But then this procedure immediately tells us that I can now combine the Dalembert's principle with generalized coordinates, because generalized coordinates we had already identified as independent coordinates, which will give us the mapping between independent coordinates and the Cartesian coordinates. Okay. So, if we put these two together, then we get what is called as the Lagrangian equations of motion, and Lagrangian equations of motion will make the procedure of finding equations of motions extremely easy. We will see that in the examples towards the end. Okay. Again, this is a lengthy derivation, and remember, in this derivation we have to always remember that we are working in the state space, which means all these quantities are treated as functions of not only coordinates, but also the velocities and the time. Okay. Let me begin by writing down the Dalembert's principle here, which we have already seen, and this Dalembert's principle only talks about the applied forces. And if the system has k holonomic constraints, then we know that for the capital N particles we had 3 n Cartesian coordinates minus the number of holonomic constraints, that is k in this case. 3 n minus k are the total degrees of freedom for this system, and I will denote it by small n, and what we need is small n generalized coordinates, and I will denote those by q 1, q 2 and so on up to q n. And in the successive derivation, many places we may have to write function of q 1, q 2 and q n up to q n. I will use a short form for it and just write q, and if I write q, that means I am actually talking about the set of generalized coordinates, which is q 1 to q n. Okay. Now, we already have the transformations from the generalized coordinates to the Cartesian coordinates. So, here are the Cartesian coordinates and they are expressed in terms of the generalized coordinates. So, I will call this as transformations. Now, from these transformations I can immediately calculate velocity. So, velocity of ith particle, remember this is nothing but d of r I by dt. So, this is velocity of ith particle, and that we can use the chain rule, and then I get velocity equal to partial derivative of r I with respect to q j into q j dot and plus del r I by del t. And now, you see the positions or Cartesian coordinates were functions of generalized coordinates, but what about the velocity? Velocity is not only the function of coordinates, generalized coordinates, but also functions of generalized velocities, because in the expression of velocity generalized velocities appear. The only thing that is nice about it is linear in generalized coordinates. So, the velocity of the particle when expressed in terms of generalized velocities, it is linear function of generalized velocities. So, if I take the partial derivative of V I in this equation with respect to q j dot, but then we can immediately refer back to the previous equation, and from the previous equation I know that this would be equal to del R I by del q j. Okay. Once you take the derivative with respect to q j dot, the coefficient of that term will remain. This identity we will use in future. So, I am going to call this as identity number 1. Now, look at this expression. If I calculate this d by dt of del R I by del q j, then what I get is this. First, again you see, this is the entire derivation is all about use of chain rule and partial derivatives. So, when I take this derivative, what I get is this. I take the derivative of del R I by del q j with respect to q l and into dq l by dt, which is just q l dot here, okay, and one more derivative with respect to partial derivative with respect to time, because time appears explicitly. And as long as these transformations are nice in some sense, nice means they are smooth. The easiest thing that we can do is, if they are smooth, then I can interchange the order of derivatives. That means, if I take these two derivatives here, I can take del q j derivative first and then the derivative with respect to time. Same thing about this also, this term too. So, now what I am going to do is, I will write everything inside the bracket here, which is derivative with respect to q l and derivative with respect to t, and derivative with respect to q j I am going to do last. So, that comes out of the bracket here. But identify this bracket. What is this bracket here? This bracket here, oh, that is nothing but V I, just go back one step and there it is. This is exactly same as V I, it is a summation over q l, summation over L del R I by del q l into q l dot plus del R I by del t, and compare it with this equation here. There. So, this is just equal to del V I by del q j. Okay. This is a vector. This actually tells you what? If the coordinate transformations are nice, then I can actually interchange the partial derivative with respect to q j with the total derivative with respect to time. That is exactly what has happened on the right hand side there. Okay. So, that is the identity number 2. Now, look at the virtual displacements. The virtual displacements, remember, are delta R I is equal to, again by chain rule, it is del R I by del q j into delta q j. And what happened to the time term? Remember, these are virtual displacements. That means, these displacements are taken at an instant t. So, no delta t term for this one. Okay. Now, go back to the Dalembert's principle and look at the first term. One of the terms is p I dot into delta R I and then summed over I. Now, let us start analyzing this, simplifying this. The first thing I will do is write p I as m times dV by dt. Okay. Then, second step, I will take this delta R I and write it as, this is given by the equation here. Okay. Now, what I have here is this. I have m I into derivative of one function with respect to t into second function, So, think of this as your second function and V I as your first function, and write it as time derivative of mi vi into the second function, but if I take a derivative of this, then it would be derivative of vi into the second term plus vi into derivative of the second term. So, we can immediately see that I need to subtract the second term too, and if I subtract that second term, that is what we get here. Okay. So, it is mi vi into time derivative of the second term. Now, we simplify this. Now, identity number 1 goes here. This part here gets replaced by derivative of vi with respect to qj dot. Okay. And secondly, on this side I have d by dt, this term here gets replaced by the term here. And now you see what happens, something nice. So, this one here is mi vi into del vi by del qj dot, but this is nothing but del over del qj dot of half mi vi square. And similarly, on this side, this term becomes del over del qj of half mi vi square, but we identify half mi vi square. What is that? That is the kinetic energy of the ith particle. Now, if I take this summation inside, I can do that because d by dt and the partial derivatives are linear operators. So, I can take this summation inside and then substitute t is equal to sum over I half mi vi square. Okay. So, this term from the Dalembert's principle simplifies to this. All along there is a delta qj sitting outside the bracket. Now, the second term has sum over I fi vector dot delta ri. Now, this I will write here again and write down the expression for delta ri, that is nothing but partial derivative of ri with respect to qj into delta qj summed over j. Okay. And now, if you rearrange, then what you get inside this bracket here, I will call this as qj, and this qj is called as generalized force. Okay. Now, finally, what do I get? Put everything together, the first term and the second term, and the Dalembert's principle looks like this. In this case, I have summation over j. Remember, the summation over I in the kinetic energy term is over the particles. So, that goes from 1 to capital N. This summation here is over generalized coordinates. This goes from 1 to small n. Remember, small n was 3n minus k, and k was the number of holonomic constraints. So, delta qj's are independent of each other. What does that mean? This identity must be true for any arbitrary delta qj, immediately implies that each one of these coefficient brackets themselves must be 0. This is how you get these n. So, there are n equations here, these n equations. Okay. What is the nature of these equations? These are second order differential equations. You can immediately see that t will be treated as function of q dot, and then when you take a derivative of t with respect to q dot, I get first of all terms in q dot, and then I have one more time derivative with respect to that. So, basically the final equations will involve q double dots. So, these are second order n differential equations. Okay. I will take this a little further and look at only a special case. Remember, this special case includes large number of problems. So, if I can express the force on the ith particle, which is F I, as minus gradient with respect to ith coordinates or coordinates of ith particle of some potential function. So, here V is not velocity, but this is capital V. This stands for the potential. So, if our forces can be derived from some scalar potential by using this process, then I can calculate Qj immediately. Qj will be equal to minus of grad of Vi. Remember, grad is with respect to I or with respect to xi, yi, zi into del Ri by del Qj. But by chain rule, we immediately know that this is exactly equal to. So, this is exactly equal to minus of del V by del Qj. So, make a second stipulation. See, we made a first stipulation that the forces are derived from some scalar potential. I of course did not say that this is conservative force. This could be function of Ri and also time t. Remember, if it is independent of time t, then this will be conservative force. If it depends on time t, then it will not be a conservative force. However, you should be able to define some energy term there. Okay. So, first thing we do is that the forces are derived from some scalar potential, and second stipulation I will make is that if velocity is independent of Qj dot, then del V by del Qj dot is 0, and then I can now put everything together in my equation. So, because del over del Qj dot, there is a dot here, del over del Qj dot of t minus V. Remember, here the derivative of V with respect to Qj dot anyway is going to be 0, and minus del over del Qj t minus V. This one has come from your generalized force term. Okay. So, I will now define a new quantity called as Lagrangian. And this Lagrangian is defined as t minus V, and this of course will be function of all the generalized coordinates q, all the generalized velocities q dot, and also may depend on time t. And then for given this Lagrangian, I have Lagrange's equations, which are n second ordered differential equations. These are our equations of motion. Rather a lengthy derivation, but you see, when we looked at the examples of the Dalembert principle, we anyway manually did this. We started by writing everything in terms of Cartesian coordinates, then identified the independent coordinates, then looked at the coefficients of the independent coordinates and set them to 0. This derivation already has done that. So, now equations of motions can be directly obtained by applying this. We do not have to do all that lengthy procedure that we did in the examples of Dalembert's principle. Okay. Immediately we will try this for some examples. The first thing that I want to try is this must work if my system is free of any constraints. So, take for example, a single particle whose coordinates are given by x, y and z. Okay. and there is a force on this particle. So, remember, because there are no constraints, x, y, z are independent of each other. Why would not I use x, y, z as generalized coordinates? Of course, yes, I will use x, y and z as generalized coordinates. Now, the force say is given by minus of grad v, where v is some function of x, y and z. Okay. So, this is a single particle moving in a conservative force field. And let us try to find the equation of motion. First of all, the Lagrangian would be what is the kinetic energy? That is simple, it is half m x dot square plus y dot square plus z dot square, and this minus the potential. Okay, remember, potential is function of x, y and z. So, let us write down, there are 3 generalized coordinates, there will be 3 equations, 3 Lagrange's equations. The first equation for x, so this equation would be d by dt of del L over del x dot of Lagrangian minus del L over del x is equal to 0. So, let us calculate this. What is the partial derivative of Lagrangian with respect to x dot? So, that is nothing but d by dt. This is just m x dot minus del L by del x, but the first term of Lagrangian does not have any x. So, this immediately gives us plus del v by del x is equal to 0, and this gives us the equation m x double dot is equal to minus of del v by del x, but we know that that is just exactly equal to f x. There you go. We recover Newton's laws, which were written in Cartesian coordinates, which do not have any constraints written there. So, this is how the Lagrangian will give you the Newtonian equations. Here is a second example. The same single particle, see, this is what I had said in our first lecture, that when we change the coordinate system and go to a new coordinate system, then we have to do a lot of work to find the equations of motion, and I gave you the example of plane polar coordinates. So, in plane polar coordinates, the equations of motion look very different. They are not simply equal to m r double dot is equal to f r. Okay. So, here I will apply the same situation, but I am going to use cylindrical coordinates as r, theta and z. By the way, in the previous case, of course, there are 2 more equations, one for y and one for z 2. Okay. Now, in case of cylindrical coordinates, can I use them as generalized coordinates? Of course, yes. So, the Lagrangian, which is function of now the coordinates q, q dot and t. Remember, here q represents r, theta and z, q dot of course represents r dot, theta dot and z dot. This is equal to kinetic energy. How would I write kinetic energy? Oh, we already know. The radial velocity is just r dot. So, r dot square plus what is the tangential velocity? That is r theta dot. So, that is plus r theta dot square and plus z dot square and minus minus V. Now, apply what would the equation for R look like? Equation for R, that would be d by dt of del L by del R dot minus del L over del R is equal to 0. This is our first equation, and this will be equal to, or this simplifies to d by dt, and what is the derivative of Lagrangian with respect to R dot? Oh, that immediately just gives me m R dot, and everything else, of course, all other terms are independent of R dot. This minus, now when you are taking the derivative of Lagrangian with respect to R, remember, oh, there is a R in this term too. So, you should not forget that one. So, this one will just become m R theta dot square, and then there is a R here too. There is a R here too. So, that would be equal to minus. So, that will be del V over del R, and this must be equal to 0, and this gives us m R double dot minus R theta dot square is equal to minus del V over del R, and what is that? That is nothing but R component of the force. So, that is del V by del R is F R. What about theta equation? Okay. So, let us derive this theta equation too. Equation for theta is d by dt of del L over del theta dot minus del L over del theta, and this must be equal to 0, and calculate this. So, theta dot only appears in the second term here. So, this will be equal to d by dt of, so, m R square theta dot and plus, now remember theta does not appear in the kinetic energy part, theta only appears in the potential part. So, this will be equal to del V by del theta equal to 0. Fine. And what is this del V by del theta? Can you make a guess? This is of course the angular momentum of the particle about the given origin. So, this is nothing but d by dt of angular momentum. Remember, this is capital L, not the curly L that we are using for Lagrangian. So, this is angular momentum, and this will be equal to what would be del V by del theta. This is nothing but 1 over R. So, I will write it as R into del V by R times del theta. This is nothing but R f theta, sorry, with a minus sign. And what is R into the tangential force? This is in fact torque. So, the second equation we get is dl by dt is equal to torque and the force. And what about the z equation? That is straightforward, that we already know. That would look exactly same as the Cartesian coordinates that we used earlier. So, that equation simply comes to mz double dot is equal to fz. One more application of Lagrange's equations. This is one of the problems we have looked at earlier, and remember the amount of work we had to do to solve this problem. This is the one with the Riemann constraint, where the trolley from which the pendulum is suspended, this trolley is moving with some predetermined function of t. So, this distance is given by f of t. Okay. Now, since you remember this example, I will quickly write down here the generalized coordinate that I am going to use is angle theta, and the Cartesian coordinates of this bob are x and y. So, I will immediately write down the transformation equations. Transformation equations would be x is equal to f plus L sin theta and y is equal to L cos theta. I can immediately calculate the derivatives of this. So, your x dot is f dot plus L cos theta times theta dot, and your y dot is minus L sin theta times theta dot. Now, write down the Lagrangian. What is the kinetic energy term? It is half m x dot square plus y dot square and minus the potential energy. What is the potential energy here? That is minus of mg y. Remember, y points down. So, the potential energy is minus mg y. Now, write this in terms of the generalized coordinate theta. So, that would be half m, and this would give you f dot square plus 2 times L times cos theta f dot theta dot plus I would get L square cos square term as a coefficient of theta dot square, which is coming from here, and L square sin square theta coming from the second equation. We can immediately see that this adds to L square theta dot square and plus m g times L cos theta. Okay. Now, let me do steps one by one. First thing we will calculate is del L over del theta dot. Del L over del theta dot is nothing but, remember, f is independent of theta dot. So, the first term will go away, then we get m. So, that would be m L cos theta into f dot. That is coming from here. You take a derivative with respect to theta dot and you would get the coefficient, and plus m L square theta dot. Okay. This is one term, and when you take a time derivative of this, so d by dt of del L over del theta dot, this will give us d by dt of m L square theta dot plus, so I will immediately simplify it here itself. It will be m L square theta double dot plus, now I will get two terms there. Remember, you have, this is a total time derivative, that means I must do m L cos theta times f double dot and plus it will be m L minus sin theta into f dot and theta dot. Okay. And also look at del L over del theta. Remember, now theta appears in several places. So, in the Lagrangian, theta appears here and theta appears here. So, you get two terms there. So, I will get the derivative of this will be m L f dot theta dot into minus sin theta minus m g L sin theta. And when you equate these two, this term here cancels with this term. That leaves us with ml square theta double dot plus, so I will take this to the other side. So, m g L sin theta, and this will be equal to minus m L cos theta into f double dot. And there you see, we get the final equation, which is theta double dot plus g by L sin theta is equal to minus f double dot by L cos theta. This is the equation we had derived earlier, and remember the amount of work that we had to do, but with the Lagrangian this becomes very easy. So, you see, we obtained these equations very quickly from the Lagrangian. This is a great utility of the Lagrangian mechanics. I am going to look at the detailed examples of the Lagrangian mechanics and how we extend it to include dissipation or even velocity dependent forces. Remember, velocity dependent forces are important. Magnetic force is velocity dependent force. So, those forces are also important. So, all that extension including applications I am going to do in third week. In the second week, what we will do is we will derive the Lagrange's equations, but from a more aesthetically pleasing, more elegant principle called as Hamilton's principle.